Thank you, Martina, and great to have a few to this very last session of the day. I know this is tough because there's all kinds of parties awaiting you down in the exhibition site, etc. But we'll make it through. My function is just to say a few words at the very beginning, and I already did say or wanted to say welcome. That should be the first chart when it comes up. And what we're trying to do is tackle an issue which is very central to the way we do space projects. Project management, system engineering, system architecting are some of the core competencies for space, incidentally, not just for space, but for all complex industrial developments. And we run in a potential crisis. The crisis is there is not sufficient supply of experienced system engineers, system architects, and that's the reason why we are making this panel today, this plenary today. So we're trying to tackle this issue from all kinds of points of views, and let's have the first slide, which is supposed, I think, my background. You have it probably seen already, so we can skip it and go on to my first chart just to give you, well, if it works. What do these systems have in common? A mobile phone, a tractor, a washing machine. Where is it? It should be on the right-hand screen. I have seen it, but it's not there yet. The question is, simple things like a tractor or a mobile telephone or a car, an aircraft or a satellite, what are they characterized by? First thing, they all need multidisciplinary cooperation of specialists, system integrators and managers at equipment, subsystem, and system level to become valid. Most of them have become complex, interdependent, self-adapting, and particularly software-defined system of systems. And this may have some surprises for you that all of those, even simple washing machines, are today strongly driven by software, because the functionality, the interface to the users is mostly in all those systems determined by software, and that was not so the case 20 years ago. So, the background of this plenary is we had a first Systems Workforce Summit at a very high level with fantastic participants, and the focus then was on social, economic, industrial transformations, which we go through, and the critical functions that we're discussing this afternoon for space for those kind of industries and products. The major outcome of the summit was that multidisciplinary system workforces are scarce, require development, and are crucial for these transformations in broader sense. Think of energy, think of transportation, think of any of those transformations which we're going through in Europe, in the US, in China, and everywhere else. So, the principal space life cycle phases are, we go through a phase 0, or we go through mission ideas, trying to figure these out as to exactly what's the best way to go to Pluto or to figure out a constellation in low Earth orbit. We then move into concept feasibility discussions, go through definition and detailed design implementation plans. Then we go do it. Where then does system architecting fit in? System architecting fits into the early phases. So the early phases, some of them say, are the early phases of the system engineering end-to-end life cycle. This is a definition question, and there's not everybody on the same line, but the key that we're trying to do on the technical side is develop a system end-to-end and define that at the early phases, which you see here in green. So, how will we run this plenary? We will have a number of short viewpoints, really short viewpoints from academia, from industry, from agencies. And the outcome of this session will be a call for action, because we'd like to create some action out of these discussions, out of this plenary today, and hopefully a call for action which will spread through the community, the space community, and be heard of, and will create some impact. That's the key to it. I pre-warn you here, this call for action will be on the tables here and there, and you will get a chance, if you agree, to sign it off as well, endorse it as you like. So, our first speaker is Professor Dr. Daniel Hastings from MIT. You have him full scale there, and please then join us up here.
So, thank you, Heinz. I'm going to speak as an academic and talk about what I see as some of the issues with, let's call it a current or modern view of system engineering, system architecture. But let me illustrate that by pointing out that, many people have now pointed out that we're in the third age of space, driven by a great many entrepreneurial efforts in space, and of course reduced launch costs, right? And what you see is the growth of large-scale space architectures, of which obviously Starlink is a prime example, but there are others on the books, where these are decentralized architectures and where the functions that they provide are not resident in a single satellite, but are actually spread within the system architecture itself. And they provide many powerful functions, to people. The second thing to note about them is that they're basically all flying computers. Now, unlike on the Earth, where the computers are stationary, they don't move. Here, they're all moving through each other, right? And so it really, really matters that they know where they are and they know how to communicate with the other computers that are around them, which points out that the issues of cybersecurity and robustness are just really, really important for these systems as well. The third thing to point out is that for reasons of national sovereignty, the idea that one nation, there's only going to be one nation which has these complex architectures is just a figment. I mean, China's already announced a whole set of constellations. Other countries will do the same thing. And that will occur for reasons of national sovereignty. So what's also important in terms of thinking about architecting, system architecting, is both the fact that you have to think about the computer science issues, you have to think about cybersecurity issues, and you have to think about the international issues associated with them, because since these systems all pass through each other, they better be talking to each other. Otherwise, what you end up with is something in space that will be catastrophic. So I'm going to argue that a modern development of system architecting has to take into account all of those things. System engineers, as traditionally defined, had better be talking to computer scientists, as traditionally defined, and to come up with a way to think about these, what are fundamentally moving cyber-physical systems with international components actually associated with them. And that is part of the future of what will matter for the space business.
Thank you, Dan. Our next contribution is from Emma Sparks. You can see her passion on this one, also her background. She is on vacation because it seems to be vacation in Australia at the moment. She sits in England at the moment, but she sent us a video, and can we have the video, please, right now?
It's my pleasure to be involved in this plenary session of the IAC Global Networking Forum. My name is Professor Emma Sparks. I'm the Rector and Dean at UNSW Canberra in Australia. I want to focus on the critical challenge facing our industry in terms of education and competency requirements for the future space systems workforce. As we navigate the complexities of modern space programs, it's evident that multidisciplinary system workforces are key to our success. These competencies are not only scarce, but also require continuous development to keep pace with technological advancements and market demands. Our space systems have evolved into complex, interdependent ecosystems, necessitating the integration of social, environmental, business, regulatory, engineering and technology competencies. To ensure the availability of skilled systems architects and engineers, we must focus on embedding a systems mindset from an early age and throughout someone's learning journey. There are many ways that this can be achieved, which lay the foundation for early systems thinking. These interventions should be interdisciplinary and focused on problem-solving exercises. At the university level, system fundamentals should be taught across fields to generate foundational systems knowledge and team capabilities. These are not skills that are limited to engineering. These are the basis of the way in which people think about problems and ways to solve and resolve them. This also requires educators to receive periodic training to stay updated on recent developments in the field. Real-world problem-solving practices, such as capstone projects, are a wonderful route for acquiring systems competencies. These projects should be accompanied by periodic systems-level reviews conducted by experienced staff to address cross-cutting systems issues. Furthermore, practicing systems engineers must remain current on their competencies by adopting evolving technologies, tools, and system practices. Industry and government employers should encourage continued learning by offering opportunities to deepen or broaden employees' systems knowledge and experience. Systems careers often evolve from special disciplines to subsystems and systems integration competencies, eventually leading to roles such as system architect, chief engineer, or project manager. To ensure the availability of our future space systems workforce, a paradigm shift is needed in schools, universities, industry, and governments. This includes adapting curricula, generating additional postgraduate offerings, and implementing training concepts with priority. In summary, this call for action appeals to academia, industry, government agencies, and professional organisations to join forces and implement these recommendations. By doing so, we can ensure that space systems architecting and engineering workforce will be available to realise our future space ambitions. I very much look forward to the discussions today.
Thank you, Emma. Enjoy your holidays. We're now switching from academia to industry, and our first speaker is Chiara Pedersoli, who is the CEO of OHB Systems, the largest company within the OHB group. Chiara.
Thank you very much. I would like to give you a little bit of an overview of OHB and the way actually we have transitioned from being a startup at the beginning, 44 years ago, and then a subsystem equipment, subsystem supplier into a large system integrator for our customers. We have transitioned from really a very small company, 5 employees at the beginning, then 10, to what we are now. We're with about 1,600 engineers in Germany, between Bremen and Oberpfaffenhofen, close to Munich. How the journey has started, we had as one of our founders, Professor Manfred Fuchs, someone with a very clear vision. He was himself a system engineer with a lot of experience in exactly the phases that Professor Stöver has identified as the phases where really the real system engineering happens. He used to work in pre-development in his engineering life, and I think that this has really shaped the approach that is brought into the company, and we have been really profiting as an organization at the very beginning from this clear vision, from a clear goal and a target of wanting to become a lead system integrator in Germany, and this has been always the goal of OHB up until one day. In the early 2000s, when we won a constellation for our German armies called Saarlupe, a radar constellation, and this has enabled then OHB to really develop consistently and concretely into a large system operator. And how we did this was really under the guidance of Professor Fuchs to start from the system architecture first. We had the luck with this first mission to be able to be responsible not only of the satellite part, but also of the ground segment, and have a big influence on the user segment as well. And this has allowed us at the very beginning to be able to have an end-to-end, the possibility to design an end-to-end architecture, and then from there to break it down into the different elements and to develop ourselves as an organization towards this goal. And this has brought us then to being in a position to develop then obviously other projects with Galileo, with MTG, and up to now where we won one of my heart projects, which is LISA. I hope that the other colleagues will not be upset, but I think it's an incredible mission. We are just at the beginning, but I'm really looking forward. And it's exactly this type of challenges and this DNA of the company starting really for a very strong system engineering, which has allowed to become what we are now. Obviously, this since the times of Saarlupe, we have adapted our organization, and this is really key to be able to introduce system thinking also in an organization, to be able to position the system engineers and the subsystem architects very closely, in my opinion, to the engineering disciplines, in order to have a very direct exchange between the actual detail work and the work at system level. And this we have implemented through and through in our projects. And this, coupled to the improvement of our, let's say, technological infrastructure, and implementing then a specific enterprise architecture, digital engineering, and continuous learning, has allowed us to reach the level we've got now. As obviously the journey is not finished. We have a lot of challenges in front of us. I mean, I know the constellations are everywhere. I mean, for us, hopefully the first ones will come too, and this will be the next step. And we have also invested as a company, and we continue investing in continuous learning of our employees. We have now started, for instance, an internal course for chief engineers, and I think that investing as a company to maintain this type of thinking and to being able to bring it into all the projects and to reflect it in every decision that we take is going to be fundamental to keep growing. Thank you very much.
Thank you, Chiara. I can attest that from a subsystem supplier to a system company was a tough trajectory, but one that OHB has managed fantastically. Our next speaker is Paul Nielsen, Dr. Paul Nielsen, with the background which you see here. Paul, floor is yours. I think this is.
Well, I have the slide, just to make sure, because it wasn't announced, I have the Slido system here for people that want to ask questions, but I don't know if they have the QRC code for that right now, but you can hold that for now. Okay, so yeah, so it's some wonderful things have already been said, and some of that was what I was going to say. But I will say, you know, the systems we build today are more complicated, more complex, and more connected than systems ever were in the past. That's where the frontier of a lot of our design is making them complex, complicated, and connected, especially that connected part. This is true of systems both in the big and the small. On the small side, NVIDIA's GPU is a very complex system. On the big side, Starlink is a constellation, is a major complicated system with lots of things going on there. And the global financial system too. I mean, you can think of almost everything from the small to the big. They have all these features now. Now, when we build these systems, as you know, sometimes there are faults, vulnerabilities, unintended actions, and emergent behavior. And sometimes it all comes together and it's just magic and everything works well. That's what we hope for each time, right? Now, many systems, perhaps almost all of them now, have become cyber-physical systems. A lot of functionality resides in the software, but the software can't do it all alone. It's got to sense stuff, it's got to act on things. So we have cyber-physical systems. And that's why software engineering and system engineering are so complementary now and so important for each other. Now, they have many similar concerns, but they're different origins, the different way they look at problems, and the evolution is actually an advantage for all of us because they can help each other, because they arose from different ways, they can highlight different features that each system needs to have. Some of the things that they worry about together are, architecture, as Heinz said, architecture. That's so important in both system and software engineering. But also model-based approaches, formalisms, security engineering, and the human interface and experience are really important in all these systems. Now, system engineering is strongly rooted in physical science and engineering. That's where they originated. But now so much functionality is in software that it has to include the software aspects of this too. And software engineering, at the same time, it also worries about complexity, modularity, open system kind of concepts, iterative development, integration and deployment, which is a real hot thing right now, AI, and the interaction with the physical world. So you see how these both complement each other as we go through. Now, space in particular can benefit from all of this. You know, in my era working on spacecraft, we didn't ever go up to fix things. Now we do sometimes, but you could always change the software. You can also change the ground software. So sometimes software allows us to continuously improve our systems, both on orbit and as a constellation, okay? That's something that we really need to think about. Also, with space systems, we often have to do, because of latency, because of the time of communications, we often have to have things done on board. Okay? And on board, they don't have all the resources we might have on Earth or some other place. So edge computing and concepts in software engineering about looking at things on the edge with more limited computational power are very important as we go forward. Now, I'm going to close now by just saying we need to be mindful about all these issues. We need to be audacious in what we try to do in space. That's one of the fun things about space is we can be pretty audacious about what we do. And we also have to be humble in our current understanding of how to address these problems. But most importantly, I think, we need to think about, we need new technology, new processes and procedures, but especially we need to rely on each other as we go forward. Thank you.
Thank you, Paul. One message I have with my scars on my back is software needs to be there from the very first moment on the architecture side. And that was not the way we did it 10 or 20 years ago. Our next speaker is also on vacation, and she sent us a video. This is Kerry Lunny. She's a technical director in Thales, Australia. Very experienced system engineer, done a lot of projects successfully implemented. So she sent us a message, a video, and I hope we can have that video just right now.
Hello everyone. Let's talk about large systems, that is systems of systems. When we have multiple independent systems, for example, space system, mission control system, the communications and tracking system, and the services and training systems, all need to work together in the formation of a space station. Each has its own owner, its own purpose, its own life cycle. Yet, collectively, they must deliver outcomes of a space station. Consider now the challenges to be tackled by systems architects and engineers. There is interdependence without control. No single authority directs all subsystems, making alignment difficult. There is often conflict and varying operational priorities between the overarching system's operations and the individual system's operations. There may be unexpected emergent behaviors. Sometimes they're breakthroughs, which is great, and sometimes they're failures. And there is constant evolution. While one system might be upgrading, other systems lag, creating mismatches, vulnerabilities, and technical debt. Now, if this is not enough, there is new frontiers of complexity. Engineering specialties are of increasing importance. Consider cybersecurity, safety, human factors, reliability, eco-design, to name a few. All need to collaborate with each other, even though they speak different languages. All want to be optimized, but at best they can only be balanced across the whole system of system. Now, if that's not enough, consider the new enabling technologies, autonomy, AI, quantum computing, digital twins, simulation, and so forth. All are adding layers of unpredictability, dynamic interactions, and/or continuous situational changes. And if that's not enough, we have some organizational challenges. Contract boundaries often mean that each supplier only focuses on their system, even though true performance depends on those connections between these systems. And while industry pushes for agility, the contract structures and frameworks makes it extremely hard to respond and adapt quickly. This is where systems architects and engineers play a critical role. Key competencies are evolving. Continuous learning is essential, whether it's mastering new digital engineering tools, understanding AI-driven analytics, or integrating model-based approaches. Now I have created the stalactite skills model derived from the common T-based skill model. The difference here is that you need moderate to deep expertise across different engineering disciplines and technologies, typically 3 to 7, and largely those related to engineering specialties and those new enabling technologies for space-related systems. Systems engineers, therefore, must have the skills to connect the disciplines, bridge those boundaries, master those software-defined systems and digital technologies, and address engineering specialties, all while creating an environment where adaptation is possible. Acquiring such competencies requires continuous learning commitment across their career. On that note, I thank you for your time.
Thank you, Carrie, and again, enjoy your vacation. Now, we're shifting from academia, industry viewpoints to the viewpoint of government agencies. And I'd like to have Larry James, Lieutenant General, retired, to come up here. He's a famous man in many ways, like most of us. Larry.
Wow. Okay. And let's see. Good afternoon. And again, it's a privilege to be here and talk about really, as we've all annotated and mentioned, that this is a complex problem that we have to deal with in this environment. Let's see if this works. So, a lot of this is an example from my previous life at JPL. I highlight a Voyager spacecraft there, which many of you will probably recognize. Humanity's first interstellar spacecraft was launched in 1977. Think of the systems engineering they had back then. It was usually, let's go buy some extra aluminum foil at the hardware store and some tape and get this thing together and make it work. But the reality is, they've made it work. And it's still sending back data 48 years later, and an incredible mission for humanity. But fast forward a bit, and you've got this thing. This is the Perseverance rover, which we landed on Mars in January of 2021. And I wanted to use this as just really the highlight for complex systems engineering of complex systems. We've heard about, large constellations and how we architect those and put them all together, and that takes a lot of complex systems engineering to make sure the ground system, the comms, the computing, all that work together. The reality is, for something like a Perseverance rover, it's all packaged in there. Extremely complex, extremely demanding challenges across a variety of disciplines, frankly. Who thinks about the Perseverance rover and thinks about astrobiology? Well, we had to, because we had high planetary protection requirements levied on us that we could not take any sort of biocontaminants to Mars, because we didn't want to contaminate the surface of Mars, and someday we go there and say, oh, there's life here. Well, it's actually life from Earth that we transported there. So again, as I'm an aerospace engineer, and I wouldn't think about biosignatures on my hardware, but we had to think about that. Okay, a nice space system. Do we think about aerodynamics? Well, guess what? With a Perseverance rover, yes, because this thing is coming down on a parachute in an aeroshell at about Mach whatever, entering the Mars atmosphere. So we have to guide it into the atmosphere. So we've got aerodynamics we have to think about. We've got a supersonic parachute we have to think about. And how are we going to integrate all that into a package? And when we first proposed this concept of the sky crane to actually land this thing successfully on Mars, on Curiosity back a decade ago, literally the NASA administrator laughed at us. Says, what are you guys thinking? But it comes down to architecting correctly up front. And I know several of our panelists have talked about that, but when you have these complex systems, you really have to get it right at birth. And if you don't, you're going to create birth defects, which you're going to address 7 years later or 5 years later as you're developing the project. And it's much more difficult to deal with them then. So we have a whole process at JPL that really goes through that system architecture process. It brings all the disciplines together in a room. We just noodle on it for a week or two to say, okay, I'm going to do this, but that impacts over here. So having a very strong system architecting integrated process up front as we deal with these dynamic and complex systems is really a must. We absolutely have to do that. The other piece I will just mention is, and I will go to the next slide. So we did successfully land on Mars. This is actually a selfie of the Perseverance rover using its mast with the camera on there to kind of look at the rover itself. But again, incredibly complex systems that have to work together on this vehicle. It's the mechanical system. We have to drive over unknown terrain. We have to have a system that will operate in that type of terrain. It's the sampling system, which was designed and by multiple scientists and principal investigators that all have to work together to address the mission requirements of Perseverance. You've got the scientists that are involved every day in terms of determining where we go next to take a sample. So you've got kind of the social engineering aspects of this thing that you have to put together. And I will tell you, scientists like to argue a lot, and many of them hate each other. And so, they're always fighting for their piece of the pie in terms of where are we going to go next, what are we going to sample next. So you really have to think about the social engineering components of this thing as well. And lastly, I'll end on software. I can give you a few examples where software ate our lunch. We actually had to delay a launch of the asteroid belt by a year because we couldn't get our act together on software. And so as we think about these complex systems, you have to bring the software folks together with the hardware folks together and make sure they are working together from the very beginning. And make sure, frankly, your project managers understand how to manage complex software systems, because I'll be honest, at least in my experience today, most project managers building these types of things come out of the hardware world. And frankly, they just allow someone else to think about software. They don't really deal with it very well, and it bites them in the butt many times. So again, all these things have to work together, whether it's a complex system of multiple spacecraft or whether it's an extremely complex system that's all integrated together. And these are the lessons certainly we've learned on the ground to make sure something like this works. So look forward to the comments and the questions. Thank you very much.
Thank you, Larry. And we now have someone else who could not be here for particular reasons. This is Jean-Jacques Daudin. Jean-Jacques Daudin was ESA Director General, and he's still extremely active, but for certain reasons he cannot be there. He wanted me to read a few words to you, which give his conviction in that respect. They will be on the chart, so I will go relatively quickly through them. He says, the world is changing faster and faster through successive waves of breaking technologies and successive generations of people, driven by forces of interests, mutual and conflictual, economic interests at global level, community interests at regional level, and so forth. In that world, space has taken more and more essential role, collecting and distributing more and more data from and all over the world in quasi-real time, but less and less in isolation from other sources of data collected on ground, air, high atmosphere, etc., combining these data for global and local information. Space is therefore more and more just a part of the chain of successive systems, hardwares, and softwares tailored to each customer's needs and demands for governments and private users. Expertise is made of knowledge and experience fueling imagination and creativity. Knowledge is more and more with artificial intelligence, but the people is still the reason, the problem, and the solution at the same time. The reason, since all what we're doing as humans is to make life possible on planet Earth, and long term to make humanity sustainable. The problem, since the behavior of individual humans is quite opposite to the reality of a finite planet for all successive generations of humans. And they are the solution, because human brains are the only natural resources growing on planet Earth. So people is a solution, and he is very strongly in saying system thinking must be the basis of all education and practicing in the future to address the planet Earth and space as a system, humanity as a system of generations, and short-term and long-term as a system of time, public and private as a system of solutions, the world as a system, and so forth. So that's essentially his messages, and they are broad, philosophical, but they give us something to think about, and thinking of system even broader. Going on to the next speaker, I would like to invite now Dr. Dietmar Pilz, who is a director at the European Space Agency and director at the ESTEC, the technical heart of the European Space Agency. Dietmar.
So, thank you very much. Now I have a couple of problems. Number one, there was a lot of speakers before, so basically all what I wanted to say, they already said. And number two, it's very late, and I try to tackle the second problem by being rather short. And maybe I start with what we just saw from Jean-Jacques Daudin, who was making a philosophical statement. And I can tell you, the director that I'm working, the general director that I'm working right now for, and the member states right now, they are very practical, and they say deliver, deliver, deliver. And that's also what we bring to the system engineering team, and what makes the system engineering team so important, because they want us to deliver. And the huge number of programs, I think we have right now in the making of the 50, 55, 60 programs, very complex as we have seen them today, and we want to deliver them in time, in cost, And all of this through industry. That's a specific model of the European Space Agency. We do by default nothing ourselves. We always work with industry. Therefore, we have to focus on these early phases when we define the missions, as we heard before, when we look at the architecture with our system engineers and make clear that we have the right architecture, that we have the right requirements at the very beginning. And then throughout the phases of the entire project, when we work with industry, we need to understand what they're doing in order to be able to make decisions. Because that's one of the major parts of our system engineers, of course, at the project leader level then at some point. But the system engineers, they need to be able to make that proposal to the project manager, whether we can go ahead with one area or we cannot go ahead. And this needs a lot of knowledge in the different areas of the systems, on software, on hardware, on system of systems, or what we call end-to-end system engineerings. Therefore, we have also our program on System Engineering Academy. We have a career path to have more system engineers. That's the only way how we can deliver these huge number of projects that our member states and our current Director General is expecting from us. I wanted to give one specific example. That's what Heinz asked me for, where I think this preparation phase and the system engineering was done very successful. And of course, I chose one, since we have Chiara here, that's basic both of our hearts. It's Hera, which was delivered on time last year, 7th October launched. And at the same time, it was actually not only in budget, but below budget. How was this possible? I talked to the team. I was not there. And of course, you know, there's a lot about discussion, teamwork, come together, work together. But there was also a long and excellent preparatory phase where all of the architecture was designed, all of the design was mature, and could go through the actual execution phase together with industry. The team had the models, the team knew what they want to do, and there was lots of problems as in any project. But when you are there, you can make the decisions, you can make the right decisions, and then cut corners, go forward, reach the target, be in time, deliver, deliver, deliver. Thank you very much.
Thank you, Dietmar. The message was very clear, I think. Our last speaker now, next slide, please, is Professor Stefan Schlechtrim. He represents the DLR, which is a research establishment with many, many different fields and lots of systems work. Stefan.
Heinz, thanks a lot for the introduction. Yes, hello, dear audience. Everything has been said. Wolfgang mentioned it. So basically I can go, but I would like to use the time to make some commercials for Lampolshausen and for system engineering and project management. I got addicted to project management 30 years ago. I'm 65, so with 35, I joined Rolls-Royce and they told me what to do. Actually, it was a manager von Kuhnheim who came up with the 3 Series and 5 Series BMWs, and he told us what he expects from us. And finally, he saved BMW with these nice cars, and I really carefully listened to him. But first of all, I think, who is here from Sydney? Congratulations for the city of Sydney. What a fantastic system, and you have managed to install a tap-and-go system which has direct access to my bank account, and it costs only $1. And most likely we are using satellites, which were all brought up by you. Unfortunately, you have access to my bank account, but it's only $1, so I will not even charge DLR for this expense. So great stuff. I'm really happy to be here in Sydney. Really great. I wanted to add a couple of things in project management, and one is the management of interfaces. First of all, and Wolfgang has said that, yes, we need a specification, and the chief engineer should actually make sure that all the youngsters he has to take on board say, this is the specification. And if we want to convince somebody else, we have to talk to our stakeholders when we change a specification. When you change a specification, it takes longer, yeah, and it costs more. So a chief engineer and a project leader is there to be really strict and is able to communicate with his stakeholders. Regarding interfaces, we all talk to each other, and the conference is a project also, and we want to establish a long-lasting partnership. And how can we do that? By managing interfaces. And interfaces are still, although we have KI, I'm going to tell something about it, are managed by people. So therefore, you need to think of who you get on your team. And we in DLR Lampolshausen got extremely lucky. We got somebody from Australia, graduated in Adelaide, and decided to come to Lampolshausen. By now, we have, I think, at least 4, 5, or 6 Australians working for us. Some of them go back, of course, to Sydney. Maybe I come back to Sydney also when I retire. What a nice city. And yeah, he's in the room, Justin Hardy. Justin, can you stand up? Justin Hardy is our department manager. He gives lectures in Melbourne. So whenever you have a problem and you want to have an interface with us, contact him. And now I tell you, and Justin is a much better communicator than myself when it comes to English. But now what I wanted to say is, we in DLR Lampolshausen, and please come to us. We are, I think, Europe's biggest test facility to test rocket engines which use liquid fuels. Ariane 6, thank God, flew a year from now. Took a little bit long, yeah, because of some changes maybe. But I tell you, we can be faster in the future, and we have shown it internally. This is our biggest success. And Justin was a big part of it. We have decided when you want to go fast, do it yourself. Similar to SpaceX, by the way, yeah, because when you can do things and you decide to do it by yourself, then you can go fast. We came up with the so-called Lumen project. You have seen it on many presentations here. We combined everything, turbo pumps, combustion system development. Justin, for example, is a specialist to handle combustion instabilities, which is really vital when it comes to the design, production, and operation of rocket engines. And rocket engines are still the reason for many failures, so really have to get it right at some point. We have our own engine. At the moment, it's not a flight engine. It's an engine which we can afford. We can operate it by using artificial intelligence or better machine learning, and this will make us much faster. So a handful of people managed within 2 years to operate an engine, and believe me, first we used it for the design to create, for example, a cooling system which worked right from the start all the way to a control system. And when you see how the control system is able to operate an engine, you are going to be very optimistic for future projects. So just to keep it short, everything has been said anyway. It's about interface management. Keep the specification safe. Do as much as you can in-house. Think really if you have to outsource it or if you can afford it to do it yourself. And by the end, it's all about the people. Once you have a team that can operate and do the stuff, let them go and do the job. You create fantastic people, and then you can hope that everybody gets addicted, and when the project is over, is optimistic enough to enter the next project. Thanks for listening.
Well, you've heard now a lot of pieces of advice from people who've done it and who've got a few scars. How I'd like to summarize is, if a project has good systems engineering, systems architecting, it usually is fairly successful within time specifications, etc. If it is not, it is often in trouble. That's my life experience and some of the scars I have on my back. Now, we've come to the end of the interventions from academic point of view, from the point of view of industry, from the point of view of agencies. And what I told you, we want to have a call for action. I cannot go through this call for action in detail because we don't have the time for that. What you see is that, well, you should see it in a moment, there is a set of needs and context. You've heard these points made by the one or most all of our presenters. System architecting design, that the early phases are crucial, I think is a message which have come through from practically every one of our speakers, and that acquiring system architecting, system engineering competencies is a lifelong story. And the problem is it cannot be taught at universities at the first level because universities are usually vertically oriented, but there is a change ongoing in various universities to create broader system engineering platforms across various faculties and give their students more multidisciplinary backgrounds from which they can grow into, with industries, into systems engineering, systems architecting competencies. The usual way to do that is to start in a specialization, understand a specialization, whether that's propulsion, as Flechtrim has said, or whether that's telecommunication, or whether that's thermal, or whether that's digital advances for data management, doesn't matter. Understanding one discipline in certain depth and then growing from there, according to the T model, acquiring other competencies as you go along, eventually having sufficient understanding of the cross issues to become a system engineer and eventually a system architect. That's it. If that's not enough, you become a chief engineer or a CTO, but you have the basis broad enough to understand various disciplines, eventually also coupled with some business acumen, etc., etc. So this is the call for action. There is a table back there where there's a few copies of it. I don't want you to take these copies along. Some of them are here. We will now sign it officially, all of us here on the panel. And any of you who'd like to sign it, there is on the last page a possibility to put your name down and your signature if you like. And we'd appreciate that if you feel that you want to do that. With that, I would like to call my colleagues one by one up front for us to sign it one by one. And that's the ceremony that we have to close out this session. So.